So in this video, we're going to talk about offset current used to compensate for gravity. Um, I tune this system vertically, horizontally first, so no gravitational effects. And I use the gain scheduling to adjust the proportional gain based on the inertia. That worked great, good settling, forward, reverse, no problems. But as soon as I go vertical, now gravity starts affecting um, the torque on the motor shaft. So with the center of mass about in the center, when you're straight down, there's no gravitational effect. And then at 90 degrees, you're at the worst case torque on the motor based on the center of mass and the distance moment. And when you're up here, again, you don't have the gravity affecting you, but you can see that on the rising side, I don't get the steady state very well. It's sort of a drift, you go overshoot and drift back. But when I land on the bottom, it's a perfect move. So what I'd like to do is try to compensate for the gravity using the offset so it's easier to tune. So we'll take a look at the moves we're making now. You can see, going up, it has an overshoot and then takes a while to integrate in, and then coming down, it's a perfect landing. And you can even see in the so the blue is the following error, and so here's the settling at the bottom is just a perfect landing. You get some integral wind up and overshoot on the positive direction. So you got to go through gravity. You notice the current as we're going up is much higher than when we're coming down. So you can see, of course, you need current for XL, but when you're running at a velocity, you just need current to compensate for friction and gravity. And it's still bouncing, so there's some current trying to make a correction. But it's obvious to see that the actual current is not very symmetrical, and that affects the tuning. So when we do a landing at the top, it's overshooting, not very smooth, but the landing on the bottom is perfect. So what we're going to do to take a measurement of this, I'm going to use the control panel to move so I can tweak my position here. And you can see when you're at the bottom, at the zero position, for example, you're near zero current. So as I rotate towards the top, it's going to be a 10,000 counts for 1 rev, 5,000 counts for 180 degrees, and 2,500 for 90 degrees. So I'm going to first take it up to 90 degrees. And back down a little bit, trying to take the friction and wind up out of it. So I got about 0.1 amps here. And so the sine of 90 degrees is 1. So from 0, sine of 0, with no offset, to 1, it's going to be 100 milliamps. And I'm going to take it up from 90 degrees up to 180 degrees. And when I get near the top again, I get near zero current because there's no gravity affecting this. So the parameter is this current offset parameter, and we'll take a peek at it here. 0xAE, and you can find that in the CAN object dictionary for CAN or EtherCAT. 60F6, subindex 3. It's in RAM and Flash. That's odd, but okay, just be careful you don't save it to Flash if you don't want to always apply a current. The loops will compensate it out anyways, but it's just good for allowing me to tune it. So I'm going to jog to the 90-degree worst case position where all the masses add up. If you have several links, then you're going to have to do some math. And presumably CML is on a computer, which is good at doing some math, so we can figure this all out. But you're going to adjust the offset value based on the position, and the worst case is at 90 degrees, and when you're down at the bottom or at the top, it's 0, so all places in between. And a gain schedule, and then the tuning becomes easy. So let's take a look at that. Amplifier, gain schedule. This is just for a test. You can't use the gain schedule if you're already using the gain schedule. But I'm going to use the keying parameter instead of the right parameter from CML. We'll just use the actual motor position. I'll adjust the offset. I've got a table with 9 entries, so I added 9. So you can see the position goes in increments of 625 degrees for well, here's 90, here's 45, here's 22.5, so in increments of 22.5 degrees. Sine of 22.5 degrees is going to be 0.04, 0.707 for 45 degrees, 0.9 for 22.5 plus 45. And then 90 degrees, sine of 90 is 1 times 100 milliamps. Anyways, we're gonna set the gain schedule, and I think, do you want to save the gain? Yeah, sure. Go ahead and save it. Okay. So there should be a gain schedule in here now. So we'll take a look. Right now the offset current is 0, and I'm going to enable, and I'm going to jog it negative. There, you can see the current. So this is the offset current here is changing based on my position. And let's get to worst case here, 90 degrees, and then getting down here around 45 is going to be 0.707, and getting close to 0 here, and 0 degrees. So you can see, I'll just go through the positions again. 0 degrees, worst case, 45, 90, and this whole time we want to also monitor the actual current, offset current changing. Just trying to get everything on the screen here. So, okay, 0 degrees, near 0 current, 45 degrees, 0.707, 90 degrees, sine of 90 is 1, so 100 milliamps, another 45 degrees, 0.707, and then back up around 0, and we're good to go. So I'm just going to bring it back down to the start position here. And what we're looking for is more symmetry in the tuning. And so I got some high gains for the proportional. So we'll make a move to 5,000 and back. So it's going to repeat and reverse. Okay. So instead of coming in for a nice smooth landing, I've got balanced error on both sides. So that's going to be easy to tune out. Let's take some of that integral off here. Now we should see a balance. Look at that. So nice smooth landing on the bottom. Nice smooth landing at the top. So there's sort of a gravity compensator in here, which is the offset current. And I could take my gains up a little bit here. Stiffen up the velocity loop. If my inertia mismatch is big, I can't bring this up too high, but let's add a little bit of proportional gain. Let's see if we can bring that error down even more. It's still some trap jerk disturbance. You can see a little bump here when you come in for a landing. If we use S-curve, it might be a little bit smoother. Let's give that a shot. A little bit of time. So the trajectory is real simple. Let's do 5 times the maximum acceleration and deceleration. Symmetrical with CME, asymmetrical with CML. Starting at the bottom, going up and coming down. And so let's see what you got the 4 jerk points here. We're going to smooth it out. Still a little bit of ripple here, but the landing is nice and smooth. A little bit of steady state error. Give it a little bit more stiffness. I don't know at what point we're going to hit oscillations, but the load attached, you might get a little bit more stiffness. Yeah, there's still a little bit of a bumpy ride. Let's add some more integration. So I'm just stiffening up the velocity loop here, but I have to be careful. The proportional gain will cause me to bounce with a large inertia. That's different than gravity, right? So inertia is not the same as gravity. And also a pull in the velocity loop. Let's move this out, make it a Butterworth. Give me a little bit, see what a little bit more bandwidth does. With a big inertia mismatch, you can't do this, but I can start here. I hear the crunchy now. And I'm running out of room for my proportional gain here. But we can stop it. And I can take the, whoa. All right. Let's disable before we do the low gain shift. That's a sudden change in the integral and proportional gain. Well, I'm still alive. All right, so secure the motor and the load next time. Maybe a little safety precaution is required. I'm going to stop it here. So thanks for watching. Take care.